cell phone, they also have,
All right, today we're gonna. All right, today we're gonna talk about hypothesis testing. All right, so basically within statistics and which is used for research, we want to test or at least see, what's going on with maybe with particular scenario, right? And so we want to test our hypothesis or test our thoughts as to why something is happening or compare things and see if they're below average, above average, or whatever the case may be, right? So we use hypothesis testing. So there's two ways you can do the hypothesis testing. You can use the p-value, which is what we normally use, right? When we talked about the normal distribution, right? And also the alpha, right? The significance level, right? 0.05, 0.01, zero point 0.1, right? That kind of thing. That is the p-value. You can also use the critical value, right? Which is basically looking at the critical value that's given to us as far as the data and the scenario, and then we compare that against the critical value within our tables, and our T table, right, or a Z table, right? Or maybe we do our T tables, right? And so we'll talk about the T student distribution table, which is used for, when you don't know the standard deviation of a population or of the sample, okay? And also the sample is small. So we'll get into all that, but this is really how we test our hypothesis to see if we can exclude or accept or not accept the hypothesis. Okay. All right. So introductory case, very quickly. All right. So introductory case, right? So today's called student studying hard as hardy studying. All right, it's the question at hand. Recent study asserts that over the past 5 decades, the number of hours of average college student studies each week has been steadily dropping, right? And so 1961, students invested 24 hours per week in their academic pursuits, whereas today, students study about an average of 14 hours, right? A lot of things could, go into that as far as why that is the case, right? We got technology, not to say we're smart or anything like that, but we have more resources at hand that help us, kind of learn faster, right? And so we still, in this scenario, we're still looking at say, okay, how do we compare between, previous years and the present? Okay. So dean at the school in California, right, wants to see if that is the case, right? And they basically selected 35 students randomly, hopefully, right? We was gonna do a random sample. Um, and so they select 35 students to ask about their average student time, study time per week. All right. And then what we're looking at is determine the mean study time students at our universities below 1961 national average 24 hours per week. And then we want to determine if the mean study time students at our university differs from today's national average of 14 hours per week, right? And so these are our two, what we say, research questions, right, that we're looking at, okay? We want to know, if we're different or how we differ from 1961, and then we want to know how we differ as far as the university is concerned as to the national averages to compared to the university. All right. So here we go. All right. So when you do hypothesis testing, right, you formulate a belief, right? You come up with a thought or a an opinion about something, that you're like, okay, you're not really sure, but you like to prove it, right? You like to see if it's true or not. Okay. So the formulated belief is the hypothesis itself, right? Every hypothesis confronts evidence that either substantiates or refutes it, right? You either got evidence that goes and proves it or supports it, you got evidence that doesn't support it, all right? Determine the validity of an assumption is called hypothesis testing, right? So when we do hypothesis testing, we're really trying to test the validity. We're trying to make sure that this is, something that's actual factual, true, or at least supported by the evidence, right? Empirical research, we have gone through, we've done the scientific method, we've looked at, the evidence, and we have calculated mathematically, statistically, that this is either this hypothesis either supported and we should accept the hypothesis, all right, or we should reject the hypothesis and just stick with what we call the null hypothesis, all right, the average of what's going on within the population. All right, hypothesis testing is the second type of inference that we can make about population parameters, all right? All right, so let's look at some symbology, all right? Hypothesis testing used to resolve conflicts between two competing hypotheses on a particular population of interest. One hypothesis is the null hypothesis, denoted by H0. That is the default state of nature or the status quo. So when you see this H0, that's what we call the null hypothesis. Basically, that is what is the status quo. That's what is believed to be the truth at that moment, right? Based on either the data that's been collected and actually studied, and we've taken an average of the class, and this is what it is, right? Um, and so we have the null hypothesis, right? And then on the other hand, we have the alternative hypothesis, which is denoted by the H with the small subscript A, right? Contradicts default state of nature or status quo. So this is where we come up with our own thought, right? We have the null hypothesis is like the sky is blue, right? Our alternative is that the sky is not blue, okay? We all know it's blue, but just for argument's sake, we'll say the sky is not blue, okay? We conduct a hypothesis test to determine whether or not the sample or not sample evidence contradicts the null hypothesis, right? So what we try and do is to either validate or reject the null hypothesis, right? And we will reject the null hypothesis, right? Doesn't necessarily mean we accept the alternative. We're just saying that there's not enough evidence to support us not believing the null hypothesis, okay? Our goal is to determine the null hypothesis can be rejected, right? You can make one of two decisions, right? You can reject the null, right? Or you do not reject the null, okay? Reject the null hypothesis when the sample evidence is consistent with the null hypothesis, right? For instance, right, in this example, right, criminal court, innocent, not enough evidence to convict, right? So the burden of proof or, beyond a shadow of a doubt, right? If there's enough evidence to support that this person committed this crime, then the person will be found guilty. But if there's not enough evidence, then we have to assume that the person cannot be found guilty. Doesn't mean they're not guilty. It's just that we don't have enough evidence to prove it. Okay? And so we have to kind of let them go and collect more evidence, right? And so you'll see this play out in many cases. If you watch any shows or if you keep up with that kind of thing, you'll notice that people will commit crimes or get accused of committing crimes, and nothing happens for a long time. That's because normally there's not enough evidence to prove their crime or enough evidence to take to a court proceedings to prove in a court, a court of law that this person committed this crime and is guilty of this particular crime. Okay, so we do not reject the null hypothesis when the sample evidence is not inconsistent with the null hypothesis, right? Not correct that we accept the null hypothesis, right? We don't accept the null hypothesis. We just say that we can't prove it, right? We can't, there's not enough evidence to say that this is true, okay? So we will either accept the null hypothesis or we reject the null hypothesis, but we can't say that that we that we accept the null hypothesis. We just can't say that this is true. We just know that we don't have enough evidence to either prove it or we have enough evidence to say yes, we can support that this is the null hypothesis is true. All right. Okay. Sample information may not be consistent with the null, okay? But does not prove the null hypothesis is true. All right, so when you talk about the null, right, a crucial step in the hypothesis test concerns the formulation of two competing hypotheses, right? And so we need to have a null and we need to have an alternative, right? We have the null. Normally the alternative is just the opposite of the null, right? But there's a certain way that we need to write it, okay? And so when we write that, if we say, the null is different or our alternative is different from the null, we just say, the null is it's 65 degrees outside. The alternative can be, it is not 65 degrees outside, right? We have not chosen a direction per se. We're just saying that it's not 65 degrees. We haven't stated whether or not it's below 65 or above 65, right? We're just saying that it's not 65, okay? And so we will use an equal sign, right? Because we're just saying we don't know which direction it is. We're just saying that we don't think that this null hypothesis uh is correct. Okay. And so as we look, right, if we specify with an equal sign, that means we haven't chosen a direction, right? That means there's no tail, right? If we use a less than, greater than, greater than, equal than, right? We are choosing kind of a direction, right? We're saying that, hey, yes, the null is, it's 65 degrees outside. The alternative is that it's it's less than 65 degrees outside. This is a left tail, right? Because we're choosing to be below the average, okay? Or below what it is has been established as the null hypothesis. That makes sense, right? So we would use a less than or equal to, but that is what we call a one-tail test, okay? So if you use either one of these, less than or greater than, right, it's called a one-tail test because you're deciding whether or not your alternative, right, your hypothesis is either greater than or less than the mean, okay? But if you don't really know or you're not really concerned about that, you just know that, hey, it's not 65 degrees. I just don't know what it is. I don't know if it's cold or I don't know if it's hot. I just know that it's not 65 degrees, right? So we use the equal sign, right? That's a two-tailed, right? And so remember the normal distribution, right? We have the two tails on the side, okay? Um, here, okay? Remember this, all right? There's one tail here, another tail here, okay? That's two tail, okay? This is if we say equal, okay? This is if we say equal, all right? If we say less than, right, or equal to, all right, we're saying here. So that's one tail, all right? If we're saying greater than or equal to, that's right-tailed, okay? So we're basically picking a direction based on the mean, right? Or based on our no mean, okay? All right, so the alternative hypothesis contests the status quo, right? And that's what the null hypothesis is about. It's just saying, look, I don't necessarily agree that the null is correct. And so as you write it, you're going to just say, this is the null hypothesis here, all right? We're going to say HO equal to 65. And then we're going to say HA, all right, is not equal to 65, okay? This is a two-tail because we use the equal sign, right? If we were to decide to do a one-tail, we would still say HO equal to 65, right? The alternative is less than or equal to 65. One tail, okay? All right. Same thing here. HO 65, HA equals greater than 65, okay? Still one tail, but it's right tail, okay? Because again, it's on this side, all right? This here is left tail, this here, right tail, okay? But there's still one tail, okay? So keep that in mind, right? If you use an equal sign, it's two tailed. If you use a greater than or less than sign, it's one tail, okay? All right. Um, okay, in general, follow these three steps to formulate the competing hypothesis. Identify the relevant population parameter of interest, okay? Whether that be the mean or whatever it is that we're looking at, right? Determine whether it is one tail or two tail, okay? That matters because if we do two tail, there's a slight adjustment to the formula so that we get the accurate or we use the proper value, okay? Include some form of equality sign, then all hypothesis use the alternative hypothesis to establish a claim. All right. So here's an example here. Introductory hypothesis testing. A trade group predicts that back to school spending will average $606.40 per family this year. A different economic model is needed if the prediction is wrong, right? The parameter of interest is the mean, right? Since we are interested in average back to school spending, right? So in this situation, the mean is 606.40, okay? Since we want to determine the population mean difference from the 606.40, right? That is, it's not equal to the mean, is a two-tailed test, right? So notice the language, right? A different economic need in models needed, if the prediction is wrong, okay? We're gonna determine if the population mean differs, right? We didn't say less than and equal than, we just said it's different, okay? So that tells us right there that, hey, we are using a equal sign, right? As the null, right? Because the null here, based on this, the population mean is 606 because it was given to us. And we know our alternative is that we are looking to say it's not 606, it's less or it's more. Okay, so that makes it two-tailed. All right. Another example, television research analysts pushes a test to claim that more than 50% of households will tune in for a TV episode. Specify the null and the alternative hypothesis that test the claim. Parameter of interest is P, since we're interested in the proportion of households, right? We know it's a proportion because we're using the percentage, right? We did sample proportions, population proportions a couple of weeks ago, right? Same thing, right? We're looking at a portion of the household, the population portion of the population, okay? Since the analyst wants to determine whether P is greater than 0.50, it is a one-tailed test, right? So we're saying, okay, um, if you look at the wording again, right? A claim that more or more than 50% of the households, right? That's our indication that this is a one-tailed test, right? And it's telling us which direction it wants to go in, right? So the probability, the P, right? Our null is P is less than or equal to 0.50, okay? Our alternative is P is greater than 0.50, okay? So we know that for this particular example, we are choosing a direction, okay? So when I wrote it up here, okay, could have wrote it a little more clearer, okay? So I'm gonna come mark over here. Excuse me. All right, and then, oh, excuse me. Okay, and then same thing here. Okay, okay. I apologize. All right, so as you can see from the example, right, the alternative is that it's less than or equal to 0.50, right? Because that's what they said. Okay. And then here alternative is that is greater than, right? This is what we think. We don't think that we think that it's more than 50%. Okay. All right. So as you do these particular, examples and you start doing the research, right? It's a possibility of making errors, right? Of thinking that that the null hypothesis is correct when it's not correct, or it should be accepted or be not rejected, right? And you pick the wrong thing, right? And so we have what we call type 1 error or type 2 error, right? And so if you look at the table here, right, if the decision is to reject the null hypothesis, that is a type 1 error, okay? Null hypothesis is true, right? But in all reality, right, the correct decision, right, is that the null hypothesis is false. So if we decide to reject the null, but the null is actually true, right, we have just created a type 1 error. If we do not reject the null, right, we don't reject the null, we accept the null, right, that's the correct decision, right? But the null hypothesis is actually false, okay? So that's a type 2 error, right? So again, if we reject the null, right, but it's actually uh, um, false, right, which is the right decision, it's the type 1 error, right? So we rejected it. We said, no, we don't believe that's true, right? But in actuality, it is true. That's a type 1 error. If we do reject it, right, we say, hey, we do not reject it, right? We say the null hypothesis is true, but it really is correct, right? That's a type 2 error. Okay. So just keep that in your mind, right? Type 1, we reject, but it's actually true. Type 2 is we don't reject, but it actually should be rejected. Okay, that's a type 2. So what we're always looking for is a type 1 error, right? So when we're looking for a type 1 error, this is what you'll see, right? This is called the alpha, right? Of course, type 2 error is the beta, all right? But generally, we are looking for the alpha, right? We're looking for type 1 errors, okay, which is denoted by this. So from once you start really getting into the hypothesis testing, right, and looking into different materials and resources, you'll see something like this where it's really just an A, but not really good, or just A, something like that, okay? The alpha is 0.05, right? The alpha is 0.01, okay? The alpha is 0.10, right? So the smaller the number, the more stringent the alpha, right? The more confident you are, right? The more sure you are in that you are accepting or picking the right, making the right decision about the no. Okay. So typically, as a rule, most times at the 0.05 significance level, right, which would be another thing that you hear. So you hear the alpha level, the alpha value, you hear the p value, the significance value. They're all the same, basically, interchangeable, right? So 0.05 is what is customarily used within research and widely accepted as good enough, right? Good to go 0.05 level, right? And so if you think about what we've been doing for the past few weeks, right? The 0.05 comes from here, 2.5% here, 2.5% here. Okay, so you add those two up, they give you 5%, convert that to a decimal, 0.05. All right, so that's how that comes, right? So that's why when I say it's significant, right? If it gets into here, right? Because of this alpha level, right? This is the accepted alpha level, right? 0.01 is somewhere in here where we are talking about, 99%. Because remember, this is 95%, right? Okay, this is 95% at this level here. 95%, right? That's 5% left over, right? 99% is up here. Okay. So we're basically saying, boom, we've encapsulated all this information here, right? At the 0.01 level, right? So we know that we've looked at the entire population, right? And we can make a call because we've looked at more things, all right? We've exhausted the population, right? And so we've included all the data points, right? And that's why the 0.01 is more stringent, right? And is considered a higher level of significance, right? And so you'll see 0.01 when you're really doing, high level research as pharmaceutical companies and that kind of thing. They'll use 0.01 in most R&D facilities or people that are doing the actual research because you want to make certain that you can accept or reject the null. Okay, you reject it or not reject it based off the significance level. But if you want to make certainty, right, you want to be sure, that's how you do it. Okay. All right. Let's see here. All right. So the note type 1 error with alpha. All right. The note type 2 error with the beta. All right. All right. So these two kind of work in concert. If you really think about it, right? They complement each other, right? If you're looking at, the type 1 error, right? All it is the other side of it is of the one, right? Which is the type 2 error. So if because they all equal up to 1, right? This whole thing equals up to 1. Okay. So if you are looking for the alpha 0.05, right, which is the type 1, 0.95 is the type 2, right? It's the beta, right? Because that's the other side, right? That's the other part of it that is kind of, that you're not accepting or you're rejecting or whatever the case may be. Okay. Okay. So the job of statistician is to conduct the hypothesis test for chosen value of alpha. Okay. The type 1 error. Okay. So again, we go back, type 1 error, right? You reject the null, right? But in all actuality, um, the null, right, is true, okay? In all actuality, the null is true, all right? So we take the null hypothesis, you make a type 1 error, the null hypothesis is true, okay, but you reject it, null hypothesis is false, the correct decision, right? But you didn't do that. You chose to reject the null hypothesis, okay? All right, so reject the null hypothesis, null hypothesis false, type 1 error, null hypothesis true, right? When it's not, okay? So, okay, let's see here. All right, so hypothesis testing for the population mean when the sigma is known, right? So typically as you're doing your research, you will not always know what the standard deviation is, okay? Or the sigma is, okay? Um, but if you do know, right, and if you basically, have someone's done this research before, or there's been a kind of prior pre-established sigma, you'll go ahead and you'll use that sigma as kind of your guide, right? And so if you know what this sigma is, or you have an idea what it is, right? You will do the hypothesis testing, but you will use the p-value or the critical value, okay? So, okay, this goes back to our z-test, okay? So, a test about the mean is based on the sample mean, okay? So, expected value of sample mean is equal to the mean, right? The population mean. The standard error of the sample mean is equal to the standard deviation divided by square root of n, right? And n again is the number of data points you have, or the number of objects, or whatever it is that you're looking at within your data set, right? Essential that the sampling distribution is approximately normal, right? And when we talk about approximately normal, the n needs to be more than 30, greater than or equal to 30, right? That's considered the lowest or the minimum number of data points that you need to really be sure, or to be, have some conclusive results, or really a strong belief in your results, and what's going on, right? So let the mean, the hypothesized mean, right, be the value of the population mean. Okay. So basically what we're saying is that we don't have this yet, right? We don't have this mean um for the null, right? We're just gonna assume, right, that the population mean is equal to the null, right? So the null is gonna take the value of the population mean, okay? So a large difference between the sample mean and the null mean does not mean that the hypothesis is false. It could be explained by chance, okay? So as I said before, all right, if we fall in the 95% category, right, or within two standard deviations of the mean, that's considered normal, right? Anything, it could be chance, it could be, fate, it could be whatever it is, right? There's no purposeful or any real contributing factors that we can identify with certainty that has caused this outcome, right? And so we just say it could be explained by chance, right? It's not till we get to the 0.05, right? Till we get to the tails that we say, okay, look, there's something going on. There's a purposeful factor or contributing factors that are making this happen, right? So the test statistics accounts for the variability and is evaluated as the mean is equal to the mean of the null hypothesis, right? And z, okay? So z is equal to sample mean minus the mean of the hypothesis, okay? Of the null hypothesis, excuse me, divided by the standard deviation or the sigma, all right, of the population divided by the square root of n, okay? So we use a test statistic to find the p-value, okay? And so p-value again is this, all right? That's alpha, the p-value, whatever you want to call it, okay? It's that, right? So this is the p-value, okay? So let's look at an example. P-value is the likelihood of obtaining a sample mean that is at least as extreme as the one derived from the sample, assuming that the null hypothesis is true, all right? So again, the population mean is equal to the mean of the null hypothesis, all right? Alpha is a significance level, the mine is 100%, it's a typo, okay? You need to choose an alpha before implementing a test, right? So you need to choose your significance level. You need to decide whether or not you're going to test that, okay? Right? So again, this is 95%, right? At um one, right? We can say this is 90%, right? We know this is one, this is 68%, excuse me. Okay. But we can test to choose either at this level, all right, this level or this level. Okay. But we need to choose a significance level. Like I said, usually 0.05 is what is chosen and used in most academic settings, and anything smaller than that is for that's really more stringent and really is going towards proving that whatever the null hypothesis is and whatever decision or evidence is used to support it, you can have some strong conviction and belief that that is the correct answer or the correct choice. Okay, so typically alpha equals 0.01, 0.05, or 0.10. 0.10 is pretty weak. We don't use that very often, right? Or not. It's not that it's not recommended. It's just that it's not the norm, right? So if you want to make a strong case for a particular hypothesis, right, or null hypothesis, you will pick 0.01, 0.05. As I said, 0.05 is kind of industry standard. All right. The p-value is observed probability of making a type 1 error, right? Use the p-value to make the decision, right? Reject the null hypothesis if the p-value is less than the alpha, okay? So as I was saying before, if the p-value, right, that is derived is less than your chosen p-value, 0.05, right, then you will reject the null, okay? If the p-value, right, is greater than your chosen alpha, right, then you do not reject the null. Okay. Okay. Do not reject the null. Okay. So again, if your p-value is less than the alpha, you reject the null. So all that's saying is that look, I've chosen 0.05 as my alpha, as my p-value, right? And when I've done the test statistic, my p-value that I calculated is less than 0.05. That means it's falling into this area here, and that it is significant. It's statistically significant, and that I need to go ahead and figure out, okay, what's going on here. This is a topic of interest. There's something going on here that I can look at and say, oh, okay, there's something, purposely happening, to, make this happen. If it's greater than your 0.05, right, then I'm going to say that it falls here in that 95% here. And then it's just normal. It's by chance. It's by, we don't know. Okay. We have no idea how it happened. So we don't reject the null. Okay. So that's your rules. Okay. All right. The p-value depends on the specification of the alternative hypothesis, all right? The mean of the null hypothesis is hypothesized by the population mean, okay? And this is the test statistic, okay? So when you're looking at everything, right? So here, all right, you got a little table, right? Alternative hypothesis, okay? Right, tell probability, right? Again, the mean of the population, right, is greater than the mean of the null hypothesis, okay? Basically, what you're saying, right, is that the null hypothesis is not gonna get rejected because it's by chance. I really don't know. There's nothing special here, right? Nothing's happening here. But here, right, the mean population mean is less than the null, right? There's something happening here, okay? And so we will kind of take a look at it. Actually, no, let me tell you. No, I take that back. I'm sorry. This is just the nomenclature for the writing, the symbology for uh the um the null hypothesis and the alternative hypothesis. I apologize, I jumped the gun, alright? So if you're going right tail, the mean is greater than the hypothesized mean. If you're going for a left tail, it's less than. If you're not going for anyone, you're just saying, look, I don't know, I just know it's different, then you are going to use the two-tail probability in the equal sign or not equal sign, okay? Or not equal sign, because you're saying the null is equal. All right, so this is what it kind of looks like I said already, right? Left tail, right tail, then two tail, okay? Same thing I drew up there earlier, okay? So this is when the sigma is known. And so as a kind of a guide, I stuck a Word document on week 6, somewhere on Moodle. It kind of gives you an idea or helps you figure out, okay, how do I write this stuff, right? How do I know if it's left tail, right tail, one tail, two tail, okay? All right, so 4-step procedure basically is specify the null and alternative hypothesis, specify the significance level, calculate the test statistics and the p-value, and then state the conclusion, interpret the results, okay? So basically, you're gonna say what the null is, right, which will be given to you for the most part, and then you're gonna come up with the alternative, it's just the opposite of the null, right? You're gonna specify which significance level you wanna use, either 0.05, 0.01, right? You wanna know, and basically, you're picking your level of significance, right? How much confidence do I have in where the particular whether or not I can reject or not reject the null, right? Calculate the test statistic and then you use the p-value, right? So as an example, right, a sample of 30 households show that the sample mean of back to school spending is $622.85, okay? It is believed that back to school spending is normally distributed with a population standard deviation of $65, right? So you have the standard deviation, right? And as I said before, the best thing is to start writing this stuff down, right, as they give it to you, okay? So you have the standard deviation, you have the null, right? Not the null, you have the test, the sample, right? Mean, okay? And then you have your null, okay? 606, right? Average which detects the average back to school spending different from 606 per family predicted by a trade group at the 5% significance level, right? So here is where you're getting your null and your alternative, right? Because this is what I'm trying to test. All right, this is what's given to us as just the status quo, all right? But here, right, it says 606.40, right? That is the mean that's given to us for the null, all right? And we're saying, or this particular example is saying, which to tell the average back to it differs, right? So notice the wording, right? Differ from the 606.40, right? We're not saying it's less than or equal to that, we're just saying it's just different, right? And so that indicates to me that we need to use the equal and not equal, right? The null is saying the mean is equal to 606.4. The alternative is saying that the mean is not equal to 606.4. Okay. We're going to specify the significance level at 0.05, okay, as indicated up there, right? 5%. Okay. And then we use our test statistics and the p-value, right? So we calculate the test statistic, right? Z equals 622.85, you know, where we get 622.85, right up here, okay? That's where we got it from, right? And if you go back to the formula here, all right, okay, that is our sample mean, okay? So the sample mean, 622.85, okay, minus 606.40, which is the null hypothesis, right? Okay, the null mean the null hypothesis mean, okay? Divided by 65, okay? All right, what's 65? The standard deviation, all right? Divided by, or the sigma, divided by the square root of 30, which is the n, okay? So for two-tailed test, the p-value is 2p, right? Why are they doing a two-tailed test? Okay, yeah, that's right, okay, I'm sorry, just making sure. Two-tailed test, the p-value is 2p, z is greater than or equal to 1.39, okay? So backtrack a little bit, all right? So we did all the math, we got 1.39, okay? So what do we do now, right? We take the 1.39 because that's our z-score, right? We go back to our trusty z-table, okay? We find our z-table, we find 1.39, right? It's positive, so we go to the positive side. We go 1.3 with 0.09, which is gives us 0.9177, right? 0.9177. So 1.3 and 0.09, where those two intersect, is our value, right? We multiply that by one, we subtract that from one, excuse me, because we want to know greater than, right? We want to know everything that's to the right of it, okay? We want to know everything is to the right, okay? So we have to subtract it from one, and that gives us 0.0823. But we're not done yet, right? Because it's two-tailed, we have to multiply by two, okay? So now we multiply this p-value that we got here, we multiply by two because of the two-tailed test, that gives us 0.1646, right? And because 0.6146 is greater than 0.05, we don't reject the null, right? It's not significant. And so basically it's saying that, hey, this is happening by chance. I don't know, you know, it's in here somewhere. And so we can determine that our null hypothesis cannot be rejected, right? And so the data does not support the research claim, right? So we cannot conclude that average back to school pending spending, and that's the S out, back to school spending differs from 606 per family, okay? Notice, we're just saying we can't conclude whether or not it's different or not. We can't say whether it's less or more. We just don't have enough evidence, okay? So we move on, right? We don't reject the null, okay? We keep it safe. All right. If we're looking for the confidence interval, of course, that's the range, right? Okay. Our sample mean plus or minus the z alpha divided by two. Because again, we're looking at a two-tailed, right? We're looking at both sides, so we need to make sure that we account for that. All right. All right. Or we can use this formula with just the absolute value brackets, and we calculate the confidence interval. Okay. All right. So as you can tell, confidence interval sometimes for conducting two-tailed tests. If that particular value doesn't fall within that range, right, then we can say, okay, hey, it doesn't fall within the range, so reject it. Okay. Reject it. If it falls within the range, don't reject it. Okay. So basically, it's saying if it falls out here, right? So remember when we did the standard deviation, we did, the plus or minus whatever, right? And if it falls outside of this range here, then we reject it. But if it falls in here, we don't reject it. Okay. All right. So this is really speaking to the raw data here, right? The mean, right? The sample mean plus or minus the z and the subscript alpha divided by two. Okay. So you go to the z table and you look for whatever the alpha is divided by two. You take the alpha, let's just say the alpha is 0.05. 0.05 divided by 2 is 0.0025, I believe, right? So you go to your z table and you look for 0.0025 within the body, right? 0.0025, it's not up here anyway. 0.0025 is, let's see, 0.0025 is, boom, is negative 2.81, okay? All right, so that will be the z-score we will use, right? So we use that, okay? We multiply by the sigma divided by the square root of n, right? So confidence interval, is just another way to test or to do some hypothesis testing. If it falls within, then you don't reject it. If it does not fall within the confidence interval, then you reject. Okay. All right. Another example here: researchers believe the average net worth millennials is less than 8,000. Okay, she surveys 40 millennials and determines their net worth. Right. So this is something that's given to us. Right. It is assumed that the population standing base is 500 and that the net worth is normally distributed. Right. Test the claim at the 1% significance level. Right. So we have the standard deviation. We have our significance level. All right. Let's see here. Right. Specify the null and alternative hypothesis. So let's go back here. Right. the researchers believe that the average net worth is a million is less than 8,000, right? Okay, so that is alternative, excuse me, our alternative hypothesis. The researcher believes that the mean is less than 8,000, right? So our hypothesis, our null hypothesis has to be it's greater than or equal to 8,000. Okay, everybody understand how we got that, right? All right. So whatever hypothesis or whatever thing you're stating as a researcher, that's your hypothesis. That's your alternative because the status quo is assumed to be the opposite, right? Specify the significance level, right? 1% converts to 0.01, and then you calculate the test statistic and the p-value, right? So if you use Excel, this is kind of how you go about doing it, right? Not really a big Excel fan, but nowadays we have more sophisticated software and things that we can use, right? Copilot, Gemini, ChatGPT that will kind of go through all this and calculate and show us what we need to do, okay? But say we don't do it right and we kind of go through the example, okay? We will just again, they gave us the average, right? They gave us the uh the X, right? The sample mean, okay? They gave us the sample mean, okay? Minus the null mean, okay? Which is 8,000, which we're looking at, all right? 500 standard deviation, and then 40 is the N, right? Because we have surveyed 40 millennials, that's our N, okay? All right, don't worry about this part. This is R. It's another software program. You probably won't use it. It's usually used by mathematicians, engineers, that kind of thing, right? So here we're gonna state the conclusion. Based on our math, right? And the statistic is negative 2.3673. If we go to our Z table and we look for negative 2.3673, right? So basically 2.37, okay? So negative 2.3, and then we go negative 223.7, and that gives us 2.39. Yeah, okay. And that tells us that we're at 0.0089, which they rounded up to 9, which is fine. 0.009, which is fine, okay? But this, right, is our Z score, right? So we go to the Z table and we look left, the left column, and at the top, and where those two numbers intersect, right? We always take the root, 2.3, right? And then we, as the left-hand side, left column, and then we take the remainder off the top, and where those two intersect is our value, is 0.009, okay? 0.009 is less than 0.01, okay? So we reject the null, okay? So we're basically saying that, hey, this thing is out here somewhere, okay? I mean, it's still within the normal distribution, but it's out here somewhere, and it's not by chance, okay? We can say that at the 1% significance level, the researcher can conclude that the average net worth of millennials is 8,000. So all we're doing is really saying, look, the null that we have selected, right? We reject the null, okay? And we can say with certainty that conclude the average net worth is less than 8,000. We can say that the alternative, right, it can be not accepted, but the alternative can be considered, okay? But the null we can reject, okay? Because again, the value we calculated is less than our significance level that we predetermined, okay? So we're testing at a certain level that we chose prior to. All right. So in most instances, though, you're not going to know the standard deviation, okay? And so because of that, right, you're going to use a t-test, a student's t-distribution. And so the T comes from the word student, and this is something that came about from anybody drink beer here? Anybody ever heard of Guinness? So Guinness, right, it's actual family name, right? He came up with this test so that he could test his beer because when he was making his beer, it was very inconsistent. One barrel would be great, people would love it. He'd make another barrel and it would be disgusting. Nobody would like it, right? So he was looking for consistency, right? And so as you can tell, We use this a lot in quality control, QC, okay? So, so we replace the sigma with the standard deviation from the sample, right? As to estimate the standard error of the sample mean, okay? So the sample distribution, right? Normally underlying population is normal or n is greater than 30, right? But when it comes to the t-test, right? If we use a t, we don't know what the sigma is, and or the population or the n is small, right? Typically less than 30, okay? Right? But really, the prevailing factor or the prevailing criteria is that we don't know what the standard deviation is, all right? And maybe we don't have a large n, and so we want to make sure that we don't overestimate, right? We're being a little conservative and not going, not trying to generalize too hard, right? So the test statistic for the t, right, when the sigma is unknown, is t degrees of freedom, right? And the degrees of freedom is just the n minus one, okay? Whatever the n is, it's just minus one degrees of freedom. There's a t table that we use, right? So we go back to the book again, and if you look, t distribution critical values, right? And so t degrees of freedom, right, is equal to the sample mean minus the hypothesized mean divided by the standard deviation of the sample divided by the square root of the n, okay? And degrees of freedom is equal to n minus one, all right? Okay. Again, to keep it clear in your head, it's really about, okay, do you know what the standard deviation is or do you not know? If you know, then use the z-test, right? The z-score. If you don't know, use the t-test, right? Or if you have a small n, right? You have a small sample size, use the t-test. It's just to make sure that you don't overestimate or generalize too much, right? Because the smaller the sample size, the less likely you're gonna really be sure or have or get an outcome that really reflects the population, right? Because the sample size is too small. The larger the sample size, the more you can be sure that the answer or your outcome is correct. Okay, so that's why as your sample size grows, and you can still use the t-test, but as your sample size grows, the t-test starts to approximate more as a normal distribution. Okay. All right. Um, so let's go back to the first case. The dean randomly selects 35 students and asks their average study time per week, right? Let's put the first example. From their responses, she calculated a sample mean of 16.3174 hours and a sample standard deviation of 7.2115 hours. Dean would also like to know the test mean, if the mean study time of students at her university differs from today's national average of 14 hours per week. At the 5% significance level, what is the conclusion of to this test? Okay, so we got a couple of things here, right? We got our 5%, we got significance level, okay? We have here, right? Okay, we have our hypothesis, we have our null and our alternative, right? They would like to know the mean study time of the student differs, right? So here, key point right here, differs. So we're going to use an equal sign, okay? Because we're not saying it's below, we're not saying it's above. We just want to know if it's different or not, right? We have the standard deviation, right? The sample's standard deviation, all right? So we're going to use that, and then we're going to calculate the sample mean, all right? At 16.3714, which is what is given to us, all right? So we have the no mean, and we have our mean of the sample, okay? All right, so here we write our null and our alternative, right? The null is that the mean is equal to 14 hours. The alternative is that it's not equal to 14 hours. Again, going back to the fact that we have determined that we don't necessarily know, we just think it's just different, okay? We specify the significance level, okay? And then we calculate the test statistic and the p-value. Same thing, no difference. We do the same thing as we do the z-test. There's just a slight twist because we're using the t-table, right? We're going to do a little something different, right? So here, the test statistics is 1.9444, right? So, let me see, okay. So let's just say we're going to I'm gonna show you what the difference is here. Okay, so what is my n? Okay, 35, okay? That's 35 students, okay? So what happens is here, if you use the t-test, right? We got 35 students. Although it's greater than 30, it's really a small population, right? So we decide to use the t-distribution, and we don't know what the standard deviation is. We have the sample standard deviation, but we don't have the standard deviation for our population that we're looking at, okay? All right, so what happens is you take the what you what the t that the alpha that was given, okay? Let's go back to the formula real quick, right? You take the alpha that's given, right? You got that, and then you take the degrees of freedom, n minus one, okay? So here, what we do is we look at the 35, right? Minus one, which is 34, okay? All right. And then we have our significance level at 0.05. And so we go to our t table, and what we do is we go down to the left-hand side, it'll say degrees of freedom, and we look for 34, right? So 34, where 34 and 0.05 intersect, right, will be our critical value, okay? Which happens to be 2.032 in this instance, okay? All right, so let me see here, make sure, yeah. 2.03, they don't show it here, okay? 1.944. Oh, okay, because it's one tail, excuse me. I gotta do something different. 34.994. Just wanna make sure I give you the right thing here. Yeah, 2.032. 0.02, two tail, 2. Okay, so this is two tail, okay, so 2.032. All right, we calculated, right, 1.9444, okay? Our p-value is 0.0602, okay? So here, that's what we came up with. So here they did it using the software. Hey, Shazzy.
Hey, Mr.
Okay, so if we stick with the p-value, we'll say since 0.0602 is greater than 0.05, we do not reject the null hypothesis, okay? At the 5% significance level, we can conclude that the mean study time of students at this large university in California differs from 14 hours per week, okay? So basically, if this is more, right, than our significance level, we don't reject it, okay? Do not reject the null. This is just because we're using a t statistic, right? So it's different than using a z, okay? If this was a z, right, and we had the p-value region and z test, we would we know we would still not reject it, right? We still do not reject the null hypothesis, right? Because it's greater than 0.05, okay? Okay. All right. And then the last thing is a hypothesis for the population mean proportion, which we've done before, all right? Again, if we're looking for the population proportion, and we're looking to do a hypothesis testing, just like we did with the 0.5 before, right? Then just go use the same formula, right? Z equals the mean sample proportion minus the null proportion divided by the square root of the null proportion, and 1 minus the null proportion divided by n, okay? All that underneath, right? So as an example, driven by growing public support, the legalization of marijuana in America has been moving at a very rapid rate. Today, 50%, 57% of adults say the use of marijuana should be legal, okay? So that is basically our proportion that we're looking at. Health practitioner in Ohio collects data from 200 adults, that's our N, and finds that 102 of them favor marijuana legalization, right? Health practitioner believes that the proportion of adults who favor marijuana legalization is not representative of the national proportion. Specify the competing hypothesis, right? So here we're going to use an equal sign because we're just saying that it does not reflect, right? Right? We're not saying that it's less than or equal than, we're just saying it's different, right? So we to calculate the value of the test statistic and the p-value, And at the 10% significance level, do the sample data support the health practitioners believe, right? So here, this is a really loose significance level, right? We're saying 10% or 0.01 here. So basically, it's really kind of in here somewhere, right? So again, it's loose and it's not something that we customarily use because again, it falls within two standard deviations of the mean. So it could just be by chance, it could be just anything. Okay?
It could be either 2.5 or the other 2 point, like 5, within that 5%, right?
No, it could be so if you look at the 2.5%, right? These are -2 and 2, right?
Mhm.
Anything here is significant.
Okay,
Right? That means there's some purposeful contributing factors as to why it happened.
okay,
And so we trying to figure that out. If it falls anywhere in here, that means it could be by chance. There's nothing to see, right? We just don't know.
okay.
Okay, act of God, whatever the case may be, right? So typically, we normally use an alpha or p-value of 0.05, right? When we do testing, because we're interested in knowing whether or not it crosses this threshold.
Correct.
Is really what we're trying to figure out. This one, the 0.10, it falls in here, right? It falls within this 95%. Okay, so it's like, yeah, we proven or not proven it at that level, but again, this is not anything interesting that we would necessarily consider. We could just say, yeah, we have some confidence in it, but it's not as much as we would have if we did 0.05, we did 0.01, right? At the 99% level, right? So we could say, yes, it's statistically significant at the 0.01 level, but they'd be like, it's really not saying much. They're just saying, yeah, okay, we looked at it, but
Correct.
it's kind of wishy-washy, all right? So if we look at the example here, right, our null hypothesis is again 0.507, right, 0.57, excuse me. Our alternative is not equal to 0.57. And we use the equal, not equal because we're just saying it differs, right? We're not saying it's less than, we're not saying that it's more than, we're just saying it's different, okay? And so here, because it's two-tailed, right? We run through the numbers, right? They gave us the p-value is 2p, right? Based on the z-score less than or equal to negative 1.71. So we go to our z-table here. Okay, again, we look for negative 1.71, right? We look to the left-hand column for the 1.7, and then we look for the 0.01, excuse me, which gives us
0.0872.
not yet. It gives us 0.0436, right? We get the 0.0436 because we have to multiply
Okay.
it by 2, right? Because it's two-tailed.
Okay.
Okay? When you just use the equal sign, you're saying, look, I don't know if it's less than or more than, I just know that it's different.
Okay.
Okay? And so we're gonna say the null is equal to 65, the null not equal to 65.
Okay.
I don't know what it is, but I just know that's not it.
Okay.
Okay? So because of that, we have to account for both sides, right? Because it's symmetrical, it's normally distributed, right? So we have to make sure that we account for both sides. So we would multiply this 0.04, what is it, 0.04, negative 0.0436 by 2, which gives us our 0.0872, okay? And because this is less than the 0.01 alpha that we chose, right? We reject the null, right? We could say that at that significance level, the proportion of adults with fair legalization and a while differs from the national proportion of 0.507 or 0.57, excuse me. So we can say that, hey, look, we don't know what it is, but we know that's not it, right? Based on our testing.
Why did you multiply with 2 again? Was two-tailed? Why is that so?
Because it's symmetrical, right?
Right.
And we're saying that we don't know if it's less than or equal than. We just know it's different,
Okay.
right? And so because we just know it's different, it can go in either direction, but we need to account for that. So because the normal distribution is symmetrical, right? What you do to one side, you have to do the other side, right? So you have to multiply by 2 to account for each tail.
Makes sense.
Yeah, okay? So, so that gives us the 0.0872, okay? That's less than our predetermined significance level of 0.1, right? And so if it's less than, right, we would reject it, right, which we have here. If it was more than 0.1, we would not reject the null. Okay, we would not reject this. Oh, there you go. Oh, we would not reject this. Okay, we could not. We would say, okay, we can't reject the null. So it it could be 0.57. We don't know.
Okay.
All right, we can't reject it. But in this case, we can reject it. We can say it's not this, right? It's not. This is correct. It's not that. The alternative is correct, right? I don't know what it is, but I know it's not that. Okay. Okay. That's it. That is all. Okay.
For today or is for chapter?
No, for the day.
Already?
Yeah. This was a rather short class. Because we're just doing hypothesis testing. It's pretty straightforward.
Right.
So I was gonna give you guys time to kind of work on your case studies and that kind of thing. And kind of get out of here a little early so you can do that, right? Use some class time to kind of hang out and figure that out. Okay.
Mhm.
So what I recommend is go through the PowerPoint, look it up on ChatGPT if you need to. But for the most part, when you do hypothesis testing, let's just start give you a quick rundown. Yeah, right?
Yeah, the concept.
Yeah. So when we do hypothesis testing, we're basically saying, look, I have a thought, right?
Okay.
And so my thought is that, um, we would say 55% of the population likes Christmas,
Mhm.
and something like that. Okay. And then I go out and I survey 400 people,
Mhm.
and I know my standard deviation is 500. I mean, excuse me, 20, something like that. Okay.
Mhm.
So first thing is that, okay, this is what we call our null hypothesis, H with the little zero.
Okay.
Okay. And so I'm saying, well, let's not do proportion, let's do something else. Um, let's do, let's say, yeah, sense anyway. Let me use the example they gave us in class. And then let's just say, average study time, is 14 hours or something, right?
Okay.
Okay? All right, so what I wanna know is, for our university, right, this is the national average of 14 hours. Is that correct with our university, right? So I go out and I sample our university, I sample 35 people,
Okay.
right? And it comes out to be, 12.
Okay.
Okay? So now, okay, well, now I need to figure out, okay, is this correct, right?
Okay.
Okay, so this would be my null mean, okay?
Okay.
Mean with the zero, right? When you see the zero, that just means the null,
No.
right? The null is the status quo,
Okay.
the established, accepted, whatever, right?
Okay.
So here, if I write my null hypothesis, right, I'm saying that average study time is equal to 12. Okay?
Mhm.
But I'm saying that I don't think it's equal to 12. I think it's less than that,
Okay.
right? Or I just think it's different,
Okay.
right? So I will go my HA, right? A is for alternative.
Okay.
U is not equal to 12. Okay?
Alright.
So when you're looking at just a difference, right, as far as like not picking whether it's below or above, you just know it's different, use the equal sign.
Okay.
Okay? And then the alternative, right, is always just the opposite of the null.
Okay.
Right? Pretty straightforward.
Right.
But and this would be considered two-tailed. Okay?
Okay. Because there's null and alternative, right?
No, because you haven't decided where it falls,
Oh, correct, right.
right?
You're right,
You just know it's not that,
correct,
right?
Okay.
But you know if it falls here, you know if it falls here,
correct,
right? You haven't, that's not your hypothesis. Your hypothesis is just different,
Okay.
right? So you will use the equal sign.
Okay.
So that you account for both sides, okay? And so, basically you'll go, say, okay, this is my no, this is my alternative, okay? And then you can either use your p-value or your critical value, okay?
Okay.
But you use the z-score, right? If you know the standard deviation,
correct,
okay? If you have a sample standard deviation, you can use that as the no standard deviation.
Okay.
Okay? So in most instances, you don't know, but just say you do know because the research's been done before. You got some previous data somewhere, right? Cool. All right. And so you go back and you kind of. Cool. Okay. So use this formula here.
okay,
Z is equal to minus, oh no, the sample mean, minus the mean of the hypothesis, the null hypothesis,
okay.
divided by the sigma, which is the standard deviation, divided by
Square root of sample,
square root of sample size, okay? And you use the z score, z test, because you know what the standard deviation is, okay?
right,
And or the sample size is large,
okay.
okay?
So if there's no standard deviation or the sample size is not large, then you don't use the z-score,
No, use a t-test,
t-test,
which will, which was a kind of what I was explaining when you came in,
okay,
okay? But we'll go into that in a minute.
okay,
So then here, so basically, all you're gonna do is plug and play, all right?
alright,
So here, what's my sample mean? My sample mean is 14, right?
Yeah.
My no mean is 12, okay?
Okay.
My significance level, right? My alpha
Okay.
is equal to, let's just say 0.05, okay? And then what's my n? My n is equal to, let's just say I took 35, okay? Based on what we already established
Right,
here, okay? All right, and so all we do is we just plug everything in.
right.
So z equals 14 minus 12, divided by our standard deviation of 3, which we just made up, divided by the square root of 35, okay? Then we go down here, we got 2 divided by, what's the square root of 35?
I'll make sure this is correct. Do my calculations, Professor. Square root of 35, I'm just gonna check.
Does it turn it sideways? If you turn it sideways,
Mhm.
it'll give you the proper calculator.
Then square root is,
Where is that? That should be it right there.
no, that's the y over there too.
Yeah. Yeah, that should be it.
That should be,
Yeah.
okay, so that, oh no.
That's not the right number.
Yeah, figure that out. I need to get my calculator, okay, 35. 5.916.
5.916, okay, so 3 divided by 5.196, give me what?
5.916, so hold on, 3 divided by 5.916, hold on. 0.05, 0.507, so 0.51.
0.51,
Yeah,
okay, so 2 divided by 0.51,
2 divided by 0.51, 3.9.
3.92, okay, so 3.92 is my z-score. So I go to my trusty z table here,
Right,
okay, I look for 3.9 and 2, okay?
right,
So basically it's 0.9999, okay?
okay,
All right, so my z-score is 0.99999. Okay, boom.
That's the answer.
Yeah, that's my answer, right? 0.9999. Okay, 0.9999. Okay. So.
Okay.
Because this is larger than this,
Mm-hmm.
right? Because that's my significance level.
Yeah.
Okay,
Uh-huh.
that's my p-value.
Right.
I do not reject the no.
Okay.
Okay, so I
Oh, you
don't
don't.
reject the no. I do
Because
not,
it's larger.
because it's larger. If it was smaller,
Okay.
then I would reject the no.
Okay, you will reject that.
Right? So basically what I'm saying is that whatever is happening in here, and that's just the way it is.
Correct.
Okay?
Mhm.
Okay? But because this is larger than my critical value, right? It's larger than any out here,
Mhm.
right? So I just say, hey, I don't reject the no. I don't reject this.
Okay.
Okay?
So that is correct then.
Yeah. So it's not necessarily correct. I just don't have enough evidence to prove that it's not correct.
Okay. Okay, makes
Okay?
sense.
So I have to just, I can't reject it. I have to basically keep it in the queue as, okay, it might be, right?
Okay.
And so you typically were not gonna get 0.9999 just because the standard deviation I use
Yeah.
is probably not correct. It's not right.
Okay, so the reason why we use the z-score over here is because we have standard deviation. If you didn't have standard deviation, you say we will use t-score.
We'll use the t-test.
T-test.
Right.
Okay.
Okay, so the t-test, same thing. The only difference with the t-test is that when we do the t-test, right? This is the formula for the t-test, right?
Oh, let me write that down.
Yeah. So you use the t-test when you don't know what the standard deviation is, or you don't know what the sigma is,
Right.
and or the sample size is small, typically less than 30, right?
Less than 30?
Right. But you could also use the t-test if it's more than 30, right? If you have a large sample size, that's fine, right? Because you may not know the standard deviation, but you may have a large sample size, right?
Right.
So you can use the t-test if you don't know the standard deviation, right? So the standard deviation is really the criteria, the threshold that you need to satisfy.
Right, right.
Either you have it or you don't. If you don't have it, use the t-test,
Okay.
okay?
Okay, got it.
Usually when you don't have it, it's because the sample size is small, right? And so you need to give yourself a little more wiggle room,
Correct.
right?
Makes sense.
So you use t-test, right? And the T comes from the word student's t-distribution,
Okay.
which was invented or formulated by Guinness.
Okay.
The beer people,
Right, right, right.
okay? And the beer guy, basically, he made his beer. One barrel would be good, the next barrel wouldn't be good.
Right.
So what he did was he got a lot of college students and he gave them samples of the beer. Okay? And so each sample was a different formula of how he made the beer.
Okay.
So he could determine which formula
Best formula.
was the right one. Okay?
Okay. So in this, what does the DF stand for, Professor?
Degrees of freedom. We're gonna get to that.
Okay.
Right? So the degrees of freedom, right, is basically what I was trying to explain a couple weeks ago, where when we look at the degrees of freedom, we're looking at the end, right? We're looking at our sample size, right? We're always looking at one. We're always looking at the sample, but there's always one that we're always excluded, right?
Okay.
Because we're always looking at one, right?
Okay.
So in order to use the T table, right, we say the T, the degrees of freedom, right? Degrees of freedom is equal to n minus one,
Okay.
right? In
Right.
this situation, right, the n minus one is 34,
Right.
right? So what we would do is we'd go to our table,
Okay.
okay, to our T table, right, which is
Separate table for
the separate table is T distribution right here. And what we do is we look at the degrees of freedom and we look at our p-value,
Okay.
all right, the 0.05.
Okay.
And where they intersect, that is our critical value.
Oh.
Okay, same thing, right?
Same thing. You
Right.
just replace the critical value. Okay.
Right. So the degrees of freedom is on the left-hand side, the p-value is on the top, on the T table, yep. So you go 34 and you go 0.05, okay? 34.05, 0.05 gives you 2.032, okay?
Okay.
And so because, okay. This is not a good example, but it's kind of the same thing here, because I used it, but because the 2.03, right,
Mhm.
is is less than what we calculated, okay? So the test statistic is 1.944. This will we go to the to the T table, right? The p-value 0.062, right? So here to use the p-value again, okay?
Mhm.
But since 0.062 is greater than 0.05, we do not reject the null. Okay,
Okay, which is like.
it's reverse.
It's the other way around.
It's the other way around.
Okay,
Okay,
okay.
so because 0.062 is greater, actually no, it's the same. I'm gonna take that back. I'm sorry.
Okay.
It's the same. 0.062. We cannot conclude that the mean. Yeah, 0.062. We don't reject the null.
Okay.
Same thing. Okay.
Okay.
All right. Because it's greater, right?
Okay.
If it was less than, we reject the null.
So they will give the p-value to you.
The p-value is something you choose,
Okay,
but typically, 0.05 is the
standard.
standard standard deviation. I mean standard p-value. Okay. Yep.
Got it.
Okay. So the 0.05 or so you'll hear it as the alpha, the p-value, or the significance level. They're all the same.
Okay.
All mean the same. Okay. So 0.05 or 5% is your significance level. Okay, and the 5% again we got from the two tails, right? Because this was a two-tail test because we weren't saying that we weren't saying that it's less than or below or less than or greater than. We're just saying that it's just different.
Different.
Right? So we use the equal sign, we know it's two-tailed.
Correct.
Okay?
Okay.
All right. So that R output, don't worry about that because R is a piece of software.
Right, yeah, I know about this.
Yeah, okay.
Yeah.
So all right.
Okay, so basically, both T and Z values are used for basically the same thing to determine that, hey, is the null correct or is it not, right?
Right. You either reject the null or
Okay.
you accept the null, right? So
Okay.
so what we do is we're looking for a type 1 error, okay? Let me go back here real quick. Okay. So when we are looking for, so this, the alpha, the p-value, the significance level is what we call the alpha or it's a type 1 error.
0.05?
Yeah, the 0.05, right? It's the type 1 error that we're looking for, right? Which is represented by this, right? This A, right?
Okay.
Or it's represented by the p-value,
Okay,
or it's represented by the significance value.
okay.
Okay?
Mhm.
It's all pointing towards type 1 error. And what the type 1 error is just that, okay? Type 1 error is basically saying, let's just say we reject the null, right?
Okay.
But the null is actually true, right? We shouldn't have rejected it,
Okay.
right? That's the type, you just made a type 1 error,
Oh,
okay?
after the calculations.
Yeah, after the calculations, right? And we say, hey, we reject the null,
Mhm.
but we shouldn't have done it. We should have just said, hey, I do not reject the null. I need to keep it as a viable option,
Correct.
right? You just made a type 1 error, okay? But the type 1 error is what we as researchers are looking for, right?
Okay.
This is I don't want you to get too confused because it really doesn't matter, right? So the type 1 error can be represented by the alpha, right?
Okay.
Which is, we already had that,
Right.
okay? Type 2 error is the beta, right? That's how you represent it. All it is the other side, right? If your p-value is 0.05, your significance level is 0.05,
Mhm.
that's your alpha.
Okay.
Your beta is 0.95.
Okay.
Okay?
Right.
You're just trying to
The total being 1, right?
total being 1,
Okay.
right? Because the whole thing is 1 under the normal distribution under the bell curve.
Right, right, right.
Okay? All right.
Okay.
Yeah. So the thing is that and I put a little cheat sheet on the Moodle
Okay.
on how you figure out whether to use the Z test or the T test.
Right, it's
Right.
basically the standard deviation. If you have a standard deviation, then it's like, oh, well,
Yeah.
you use the Z tail. But if you don't have the standard deviation, then you use the T
The
test.
T test, right?
Right.
Or if you have a small sample
Small
size,
sample size,
use the
yeah.
T test, right?
Right, small sample size,
Right.
understood, yeah.
You can use, if you have a large sample size, you can use either one.
Okay.
Okay? But if you don't know what the standard deviation is,
Yeah.
then you have to use the T
The T
test.
test, right, right, right.
Right?
Okay.
But if you know the standard deviation, but you have a small sample size, to be on the safe side, use the T test. Okay?
Makes sense.
Yeah, do the T
Okay.
test. All right?
All right.
But if you know what the standard deviation is, typically, if you know what the standard deviation is, you probably have a large sample size,
Okay,
then you will use the Z-test. But if you have if you know what the same deviation is, but it's a small sample size, I would go with the T-test, because as the sample size gets larger, the T-test starts to look like the Z-test. The distribution, right?
okay,
The way it falls will start become like normal,
okay,
right?
right,
T-tests are really based on the size of the sample.
Okay.
And so you can have a T-test that's, more skewed to the right or to the left, depending on what it is, right?
Right.
So because you're not sure, that's why you don't necessarily, that's why you use the T-test, because it's such a small sample size. Okay, but if you have a large sample size, the bigger the sample, the more likely you exhausted the population,
okay,
right? And so you can have more confidence in your outcome.
okay.
Right?
So my last question, Professor, is that why do you have the alternated test against why do you use that? What's the reason for that then? Why do you have HA and then no, then no? Why do you?
So
Why do you?
it's
keep that?
you're just testing your hypothesis. You're testing your thought, right?
Okay.
So and let's just say, I don't know if you want to study something, right? But I mean, what would you want to study?
Law, yeah,
Like what? Just
law, right? So criminal law.
yeah.
Yeah,
Okay. This is exactly they use this in court, right?
yeah,
In criminal court. Do we have enough evidence
correct.
to convict him?
Yeah,
No, we don't have enough evidence. We're not saying he's not guilty. We just don't have enough evidence
evidence
to prove
prove
it.
it. Right.
Right?
Correct. Yeah.
So let's go back and get more evidence.
Right.
That's what we're saying here.
Oh,
That's
okay,
what this
makes
is for.
sense. Okay.
Okay?
Okay.
So the null hypothesis would be, he's he committed the crime,
Right.
or he's not I guess he's not guilty.
Right.
No, that's not true.
He didn't commit first degree, he committed second degree murder, something like that, right?
Yeah,
Close.
something, yeah. So basically the burden of proof, whatever the case may be, right?
Mhm.
But if we're looking at, committed the crime or didn't commit the crime, all right? But that's choosing kind of left or right, right?
Okay.
I'm trying to find a neutral situation, right? Do we have enough evidence to prove this crime, right?
Right.
So that would be the no. Basically, commit the crime,
Okay.
right?
Okay.
Did not, or yeah, don't know. We don't know if he committed the crime or not.
Okay.
Right? Would be the alternative.
Oh, okay.
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 We don't know.
We don't know.
Right.
Okay.
And so it could be did commit the crime, didn't commit the crime, right?
Okay.
And so that's what this is really for, right? Testing hypothesis. Does the particular drug work or not, right?
Okay.
If the drug works, right? Right? That's yeah. So the no would be basically, does the drug work, right?
Right.
And then the alternative would be, the drug doesn't work.
Right. And to get the answer about you do more trials.
You do more trials, right? Which would be your end, right?
Right.
The more trials you do,
Right. Sample more.
those results come
Yeah.
out,
Yeah.
the more reliable those are, the
Correct.
more confident you have in the
And the
outcome.
bigger the standard deviation would be then, and then, you know what I mean? Like, right.
The standard deviation, yeah, I mean, it doesn't necessarily, it just says the data spread out a little bit more, right? It doesn't necessarily mean that it's not, a large standard deviation doesn't mean that the data is not true.
Okay.
Or that the hypothesis is not true. There's nothing to do with it. It
Okay.
just means that there's more
More data.
variability.
Right.
There's more variance
Right.
within
Okay.
the sample size, but doesn't necessarily mean that the data is not ringing true, right?
Right.
And so when we do hypothesis testing, that's all we're doing. We're just saying, oh, if we were to say, the drug works, but it works at this level,
Mhm.
right? The drug works at 65% efficacy, right?
Mhm.
I think it works at 55% efficacy, right? It's less than, right? That's a one-tailed test because I'm picking a direction.
Okay.
I'm saying it's below.
Less than, right?
Right, less than, right? So that's
Right.
one tail.
Right.
So I wouldn't need to multiply by
By
two.
Yeah.
I would just go to the Z table,
Yeah.
right? And then decide, or the T test, whichever, depending on how many samples I had.
Right.
Okay, so, the criteria you need to look at is the sample size
Mhm.
and whether or not I know the standard deviation, right? The standard deviation is really the priority here.
Right.
I know it or I don't.
Right.
If I know it, cool, I use the Z test.
Mhm.
If I don't know it, I use the T test.
Mhm.
If the sample size is large,
Mhm.
and I know the standard deviation, definitely Z-test.
Z-test, yeah.
If I have a large, what you call it, sample size, but I don't know standard deviation,
T-test.
still use the T-test, because eventually, because of large, sample size, the T-test will look like the Z-test, the
Okay.
distribution.
So if the question said like, hey, we don't know if the drug works, but we think it does, then you will use multiply by 2 because you use two tails, because you're not
Right,
going in one direction,
right.
you're going two different
Right,
directions.
you're just saying it's just different.
And if they say, oh, the drug works, then it'd be one tail.
No, we'd have to specify a level.
Okay.
We would have to say, oh, the drug, based on previous study, the drug works at 80%. You say, I don't think so. I think it works at 75%.
Okay,
That's a one tail. Or I think it works at 85%.
that's one.
You're picking a direction,
Okay,
okay? Either below or above, right? The mean. So you pick a direction. That's one tail,
okay.
right? So then you wouldn't need to multiply by 2.
Right.
Okay.
Makes sense.
Yeah. Yeah, see, so if it's known, all right,
And if there's no standard deviation, then beside the Z, there'll be a T, right, in the formula? It'll be two P, T,
no. If it was no standard deviation, you use the T.
yeah,
Yes.
right.
You use,
That's
that,
right, okay.
Yep.
Okay, makes
okay,
sense.
yeah. Just make sure you calculate the proper degrees of freedom,
Correct.
right? So the T, degrees of freedom, that is associated with, right, and the significance level. So you go degrees of freedom, significance level, right, or the alpha, or the type 1 error, or the p-value. You go to your t-table,
Right.
where they intersect, same
Right.
thing, is your what you would call it, your t, your test statistic,
Uh-huh.
and then you'll compare that to the calculated,
Given, yeah.
the given
Okay.
statistic. And if it was greater than the statistic, don't reject the no,
No.
right? But if it's less than,
You reject the
you
no.
reject the no,
Okay, that makes sense.
okay? Since 0.062 is greater, do not reject, right? Because again, it's falling within
Right.
that 95%.
Even better, more, like, let's say 0.0602 is bigger than 0.05, so it's better in results, whatever results.
It's not better. It's not better. No, it's
bigger.
It's bigger, and it's just saying that, hey, it's in here somewhere.
Okay.
Right? Which
Right.
is normal,
No,
which is by chance. I don't know what it is,
okay,
right? But if it was less than, then we know for
It's
sure
on the
that
sides,
it's on
yeah.
the sides, and that there's some reason it's happening.
Okay.
And we can manipulate that, and we can start building models off of that, because once we know that it's significant, when we start looking at, okay, what are the contributing factors now?
okay,
What makes it do it, all right?
right,
Oh, if you do this, it does that. If you do this, it does that. If you do this, it does that. Cool. What's the correlation?
correct,
Okay, and then if there's a strong correlation, then we're like, okay, cool. So there's a strong correlation. We know statistically there's a strong correlation, right? And then we start doing other things. We start doing the ANOVAs and other sequential modeling.
right,
Not important right now. So then I would know that, okay, there's something to look at here, and then we could start building the model
okay,
to try to, figure out, okay, what are the ingredients to a cake, right?
right,
When we bake a cake, we know we need certain temperature, flour,
eggs and stuff, yeah,
egg, right?
yeah,
That's gonna give us a cake,
right,
okay? We know that. That's our model,
right.
right?
Oh, yeah, okay, we know that.
Yeah, we know
That's
that.
for sure.
The rest
for
of
certain,
it, it's
yeah,
the model, right? At the end of the day,
Right.
okay? We know that for sure. But we only knew that because when we tested it out, right, the different recipes, right? If it fell within here, right, we know, okay, I have no idea how this cake came about,
you're right,
right? I tried eggs, sugar, butter.
yeah,
Then I tried eggs, honey, butter,
right,
right? Eggs, honey, butter fell in here.
correct,
Egg, sugar, butter fell in here. Oh, wait a minute, I got something now.
right,
I got the recipe,
okay.
okay? I understand what's going on.
Makes sense,
Yep.
okay.
Okay, so now I can, no matter what I do, I have a model, and as long as you follow the model, you always get the cake.
Right. And we use these hypotheses is when statistics come out to make sure that if it's certain, or if it's, if there's something different that could happen, right?
We use the hypothesis testing to test our thoughts. Test, that's why it's called hypothesis, right?
Right.
Hypothesis is, you hypothesize,
Right.
okay?
Like labs and stuff that how,
Yeah, that's how they do R&D. That's how they do research in the labs and
Yeah,
that kind of thing, right?
Chemistry, we used to do the hypothesis.
Right.
If you mix this chemical, we know for certain this is gonna happen, but if that happened, then write the hypothesis of why it didn't happen, and what's the thing that caused it to happen.
Right, we get the factors, right?
Right.
But first you gotta come up with your hypothesis, right?
Correct.
So your hypothesis is that, mixing, nitrogen and oxygen, right, gives you air,
Correct.
okay? That's what you think,
Right.
alright? But the null is that that's not it,
Right.
okay?
Right.
So that's your null. So now, okay, now you gotta prove it,
Right.
right? So then you start doing an experiment.
Correct. Right.
Okay. And so you use your based on the data you collected, right? I collected, air samples,
Mhm.
right? Sample one, 70% nitrogen, 10% oxygen,
Right.
right? Sample two, 75% nitrogen, 10% oxygen, 20% oxygen, right? So it's forth and so on, right?
Okay.
And then you calculate the mean, you
Mhm.
calculate the standard deviation,
Mhm.
right? And you have the known population
Correct.
deviation or a mean, right? And then you say, okay, what level do I want to test it at?
Okay.
All right,
Mhm.
so 0.05 is the significance level I want to test it at.
Right.
So I run my data, and then boom, if it's less than then I reject the null, and I say the alternative is that yes, it is made up of nitrogen and oxygen.
Uh-huh.
If it's greater than,
Then you don't reject them
then you just say I can't reject the null.
Right.
I have to consider this as an option.
as an option.
Right, I have to consider the null as being viable,
Why?
right? I don't know if it is or not, I just know I don't have enough evidence to say it's not.
So it's not certain, but it's like, hey, that's what it's showing with all the evidence that we have
Right,
for now.
it's pointing in that direction that I can't disregard this. Okay? You're not saying it's right or wrong, you're just saying that either I have enough evidence to say it's an option, or I don't have enough evidence to say it's an option, right? Again, I have enough evidence to say, yes, this person's guilty. I don't have enough evidence to say they're not guilty, right?
Right.
Doesn't mean they didn't commit the crime.
Right.
I just don't have enough evidence to prove it, right?
And that's when you do more evidence.
That's why you send people back, like, hey,
Yeah.
when you watch the crime shows,
Yeah.
hey, we can't take this to court.
Yeah.
This is they gonna tear us apart. We don't have enough evidence,
Right.
Or the evidence circumstantial,
Because of censure, yeah.
right?
That's true.
It's there,
Based on circumstances.
right? Based on circumstances, it's like, yeah, it's there, but this could happen to anybody. This could be, and this could be chance, right?
That's how the defense lives.
Right? It could be chance. It's like,
Yeah.
okay, just because he behaved this way, it might be a little weird, but doesn't mean that it's not a viable way to behave, right?
Correct.
You see people acting weird,
Yeah.
like sometimes they'll say, oh, this guy's wife died.
Yeah.
He's not crying though.
Why
did it.
not cry?
He
He
did
did it, yeah.
Maybe he doesn't cry. I don't know. Maybe he doesn't have any teardrops.
That's defense.
Right? I don't know. He doesn't, you know what I'm saying? I don't have enough evidence to prove that he did it,
Right.
that he's guilty of it, right? OJ is a perfect
I
example.
was gonna say that OJ Simpson's a perfect example.
Right.
What he did.
We had a lot of things that pointed towards saying like OJ might have done it, but not enough.
Not enough.
Not enough.
Right.
It didn't line up enough for us to say for certain, like, yeah, we can say OJ did it.
Yeah.
Like, no, there's not enough
It's
evidence.
circumstantial defense one because at the end they're like, oh, the glove didn't fit.
The glove didn't fit,
Yeah,
right?
right.
Okay. Not to say that OJ didn't do it, but the glove doesn't fit.
Right.
Okay. So
Makes sense.
Yeah.
Sense.
okay.
It's basically taking that critical thinking and putting it in the equation.
Somewhat. Yeah.
Right. Makes sense.
All right. That's it, my friend.
Right. Well, our group is almost done with the case study too.